how's everyone doing? Good. Is today Tuesday? Yeah, today's Tuesday. So I'm going to start. We're going to start Gibbs free energy today. We're going to talk about free energy in general. Today I'm going to talk about it in kind of a thermodynamic way, and then this is something new that I'm going to try. Eventually, this will lead us directly into equilibrium. Well, we'll do phases, but I want to talk. I'm going to spend next class, hopefully, if we get to it, approaching free energy and the idea of equilibrium kind of early on, and I want to approach it in a way that how I look at it. If you go into Atkins and look at equilibrium, they'll define this thermodynamic quantity called the chemical potential. You don't have to write this down, I just want to put it down. Where we'll measure how mass flows in a process as a function of, say, temperature or moles, mass or moles. So the idea is that, or some other variable. The idea is that the book approaches equilibrium from the idea that you have, say, some moles of reactants, and thermodynamically what's happening is those moles are flowing into moles of products, right? The moles are conserved, and imagine if you have two reactants, a mole each, that form another one, you can track how moles convert over time as a function of temperature, right? As temperature goes up, maybe they'll convert more quickly over to products. So they talk about this using what's called the chemical potential. And I really don't like this approach. It's a nice approach for thermodynamics, but it's not a very helpful approach for chemistry. So I'm going to kind of rearrange things a little bit in this class, I think. I don't have an eraser in here. I might have to go steal one from someone. Yeah, let me go grab one. Pretty sure this is my eraser anyway. Yeah, so we're not going to tackle it that way, I think. Instead, we're going to talk about equilibrium and Gibbs free energy and kind of the idea of equilibrium from a molecular perspective instead of a thermodynamic perspective. We'll talk a little bit about the thermodynamics, but I look back at my own research and my own journey through physical chemistry, and I've never used chemical potential in my entire life. I know there are probably chemical engineers in here who are probably rolling their eyes at me, because thinking about how mass flows as a function of temperature or volume or pressure is something that might be really useful for chemical engineering, but from a chemistry point of view, it's not that particularly helpful. And so we'll talk about chemistry and reactivity from an energetic point of view, but in a microscopic way. We'll talk about molecules converting from one form to another, looking at what we call the reaction coordinate of that looks like, and being able to calculate thermodynamic properties, equilibrium constants, and later rate constants using this approach. So it'll be a more microscopic approach to things instead of a macroscopic one. And I think that's a really, really powerful way to look at things and much more useful, at least qualitatively. But we're not quite there yet. I want to introduce one more thermodynamic topic, which is free energy today, because it kind of ties in everything we've learned so far. So the idea we're going to talk about is free energy. And of course, it's probably reasonable to define what free energy is. And so given a process, given a thermodynamic process, a reaction, a compression, whatever you want, the free energy change of this process is the net energy available to exploit for other purposes. Okay, so for instance, Maybe, for instance, we can consider a reaction, very simple one, A plus B goes to C to D. Right, and we can go and measure the amount of heat released from this. Let's do this at constant pressure in T, constant pressure or temperature, constant volume, whatever you would like. Let's just do constant P. Actually, let's just leave constant P. And of course, with constant P, we can measure the heat output or input, delta H. Right, as we'll see, we'll also be able to measure the entropy change. We'll talk about that first before we dig into free energy. Right? And the idea is that delta H is the total amount of heat transferred in this reaction, but delta S is the heat transferred that we cannot access directly. Right? This is the tax that Mother Nature takes. Right? This entropic change. Right? This is heat that is transferred in and out of the system to its environments or into the system, but that you can never use. Right? This is used for rearrangement. You know, the disorder of the system, however you want to look at it. Right, changing the probability distribution of the velocities and the motions of the molecules, right? It goes into that statistical part of energy change. Right, so we could maybe ask the question, what is left over in energy? And it's very natural to write, okay, well, this is the total amount of heat, and let's subtract off the heat released from delta S, from entropy. And again, by the second law, delta S is equal to the change in the heat divided by the temperature. So the change in heat is T times delta S. It should be positive, or inequalities on equals, but just bear with me. And so the energy content associated with entropy is T delta S. This is the amount of heat transferred in the system as entropy. Right? And so let's think a little bit about what the sign of this can be. So if delta H is greater than T delta S, then that means this number is positive, which means that there's some leftover energy, that there's some leftover energy, there's some positive energy remaining. Talk about what we mean by remaining in a second. And if delta H is less than T delta S, we have negative energy remaining. What does it mean to be positive or negative? Well, it means that we're looking from the perspective of the system itself. So if delta H minus T delta S is greater than 0, then the system, let me think of the right way to write this. Requires more energy in entropy than is given in heat. Is that right? No, sorry, that's incorrect. I have it flipped again. So if H minus T delta S is greater than 0, then the system, let me think about the way I want to write this. I want to get my wording right. let's come back to this for a second. Let's do some math first. So let me think about this a little bit. I know what I want to get to, but I haven't defined everything that I want to get to, so I'm jumping ahead a bit. So let's hold on to this idea for a second, H minus T delta S. So let's just do a little analysis of this equation here. Okay, so let's assume constant pressure. This is what we've assumed. All right, if it's constant pressure, then we know that the change in heat of the system is equal to the change in enthalpy. Okay, forgive this. I'm sorry. I'm trying to skip through my notes ahead a little bit, and I think it's just a bad option. So let's start over again. Let's start over again. I apologize. Yeah, I don't want to get, I know I'm going to get people lost, so let's not do that. I had a really good idea in my head, and now it's falling apart. Okay. We have an idea that we want to analyze H minus T delta S. So let's come back to that in a second. But let's start with the first law. And so let's think about a process, right? So let's, for instance, say we have a reaction inside of here at some temperature, some pressure, some volume, okay? We're able to be, and the question is that without putting any more energy into the system, maybe we end up being at a new pressure, new volume, maybe new temperature. Does this occur spontaneously? What do I mean by spontaneously? I kind of mentioned this a couple times, but let's go back to the idea. The idea of spontaneity. Spontaneous means process proceeds without additional external input of energy. Okay, so the idea is that we put A and B together, we let it sit overnight, and we come back, do we see C plus D? Right? At the given temperature, pressure, and volume that we're at. Right? So does this occur spontaneously? And the definition of spontaneity, right? Spontaneous processes satisfy the second law, which means that the change in entropy is greater than the change in heat divided by temperature. That's the first one. And we can write TdS, right? We multiply both sides by T, is greater than equal to dQ. That's the spontaneity, that the amount of entropy change is greater than the amount of heat released by the system, or absorbed, depending on which way you look at it. And of course, at constant pressure, this is equal to dH, right? Change in enthalpy, right? So the idea is that a spontaneous process occurs when the entropy change, the amount of energy generated by entropy, is greater than the change in enthalpy. So let's think a little bit about what that looks like. Let's look at two examples. examples are kind of abstract. We're going to have to kind of juggle some variables a little bit. But let's say, for instance, you have your reactor with A plus B. And let's say that this is an exothermic reaction. Which means that dH is less than 0. Right? The system releases heat to the environment. Maybe make this delta H instead. Okay, so this process is going to release heat. It's going to release enthalpy out of the box. Now that means then that the amount of energy inside the box is decreasing because it's releasing energy. So delta U inside the box decreases. Right? There's being heat, bless you. There's being heat released to the outside environment. So the entropy of the environment, the surroundings, are greater than 0. Right? That's a good thing, right? The idea is that, remember, the entropy of the universe is always increasing. So the process that introduces more entropy to the outside environment is a favorable one. And so for this to be increasing, then that must mean that the entropy inside is decreasing. But let's think about the work being done here. Right? We've left one thing, right? We talked about heat, but what about the work? Right? So the entropy inside the box is decreasing, right? The process is making the environment more ordered. But in order to think about the way this is written. So in order for the box to overcome the fact that delta S inside the box is less than 0, the system exerts less work than expected in order to overcome the energetic penalty of delta S inside the box being less than 0. So I know this is a little confusing, but the idea now is that the work being done out of the box, it's not a very good arrow, excuse me. The work that's coming out of the box is less than the total change in energy, because some of that energy has to be used for paying the entropic tax, right? A spontaneous process will always have entropy increasing, so if a process makes entropy decrease, it's an ordering process. That means you have to provide additional energy to the surroundings so that delta S of the surroundings is greater than 0. The system's not creating its own entropy. You have to create entropy somewhere. So some of the work that the system will do doesn't come out as work, but rather comes out as heat to supply the Mother Nature with its tax, with its entropy. Right? So if you have a system that is, if you have a reaction that is ordering, so let me write that down in a slightly different way. So if your reaction is delta S less than 0, an ordering reaction, say for instance taking a liquid and forming a solid, and delta H is greater than 0, then the amount of work available for the system to do is less than the total change in energy in order to ensure the delta S of the surroundings is greater than 0, right? So imagine that there were no surroundings and you do this process, nothing would happen because the entropy of the system is less than 0, which means that it's not spontaneous. But in order to drive this process forward spontaneously, the system has to release heat to the surroundings and increase the entropy, and that takes up some of the energy change being used to provide delta S, and so you get less work out, right? You get more energy out as heat. In fact, you get as entropy that you can't use, so the amount of work you get out of the system is less than what you would expect by the total change in energy. All right, so maybe let's do the opposite case, and this will become more clear. So before we do that, we can look at delta H minus T delta S. Delta S is less than 0, so this value is always going, delta S is less than 0, right? It's exothermic, there's energy being released. So this is a negative number, and this number, well, it might be, right, so you have a negative number plus a positive number, depending on the size of this, whether it's greater than 0, right? So this is greater than 0 if delta S is very negative. Right, it's a very ordering reaction. Right, so the idea is that in order for a reaction that is ordering to be spontaneous, you have to lose some energy to the universe, the surroundings, in order to satisfy the second law, delta S is greater than 0 for the outside. And so that the difference now is going to be slightly greater than 0. If delta S is a very ordering reaction. So that means a little bit of energy that you would otherwise get out of the system is lost because you have to pay Mother Nature its tax in the surroundings. All right, so let's try the opposite example. So instead, let's let delta H be greater than 0. The system's endothermic. Reaction is endothermic. It pulls energy in. So heat is coming in this way. We know that because heat's coming into the system, the entropy of the surroundings must be less than 0. And so that must mean that delta S here is greater than 0. And so the entire process, in order for it to be spontaneous, delta U needs to be less than 0. The system needs to lose energy. Right? And so let's think about that, right? So the total system needs to lose energy, net energy. But when we're putting in heat, right? So that means the energy is rising. You're pulling in entropy as heat into the system. Energy is rising, but you need a net process for it to be spontaneous. Energy has to decrease, which means that the system must put out a lot of work, right, to make up the difference. The work here is greater than delta U. So here we have delta S greater than 0, delta H greater than 0. And so let's look at E delta H minus T delta S. Well, this is positive, and the whole thing will be positive if delta S, so this is if delta S is slightly disordered. So here we have favorable conditions in some way, right? So the system's entropy is increasing, that's a good sign. And so the system has to pull in energy from the outside to fuel this entropy change. And so as a refund to the tax, right, the system, so not as a refund, the system basically, the reaction is withdrawing energy from the universe, from the surroundings, and you've got to pay it back. And so what happens then is that as you get heat coming in this way, then you're going to have more work coming out this way than the other case. And this is somewhat confusing, but the idea is that the system now has an excess of heat. Right? It's pulling in excess heat, which means it can convert that into work. Right? So if you have a system that is, right, so the idea is that if the system pulls in heat, if you have an endothermic process that pulls in heat, and it's a disordering process, something that's spontaneous internally, then the system's going to generate more energy out because you have all this excess energy. Right? The reaction creates entropy. You're pulling in heat additionally, so you have all this excess energy that you can then pay out. Meanwhile, if on the other case, the system is depleting energy in this case, so in order to be spontaneous, the system can't release that much energy as work. There's not much left over, right? Because this has to be disordering. And so in order for it to be disordering and to also release heat, you can't release as much as work. More heat gets released. So the idea is that endothermic and disordering reactions. Now, let me write this in big text because this is kind of the take-home point that I want to give. This is kind of a really nice rule of thumb. But reactions that are endothermic must be disordering to be spontaneous, and reactions that are exothermic can either be they don't must be, but can be spontaneous with disordering, or somewhat ordering. Right? So if a process is endothermic or exothermic, this is a negative number. And if the process is disordering, which means delta S is greater than 0, you have a negative number minus a negative number, so this is really negative. And as we'll see, that means it's very spontaneous. So if you have an exothermic reaction and it's disordering, it's going to always be spontaneous. But let's think about this. If it's exothermic, if this is less than 0 and this is also less than 0, this is ordering. Remember, delta S here is disordering. And delta S is less than 0 is ordering. So if delta H is less than 0 and delta S is less than 0, this is going to be a positive here. And for this whole thing to be negative, then it depends on the magnitude of delta S. Right? So some ordering reactions are spontaneous. Endothermic and ordering reactions are spontaneous, but that's because delta S is fairly small. Right? But if they're both, if this is negative, if this is exothermic and it's disordering is positive, this number is always negative, so it's always spontaneous. I remember that spontaneity Spontaneous means that T delta S is greater than delta H. That's what we derived for a spontaneous reaction. Right, which means then that TdS minus dH is greater than 0 is spontaneous. That's the opposite. So if I multiply both sides by -1, dH minus TdS less than 0 is spontaneous. So we want this number to be less than 0. What that means is that the system after it's paid its entropic toll and released or absorbed energy from the heat, is there something left over? So let me write that down here. Now this has been a little haphazard, but it'll all come together. Again, the criteria for spontaneity is that the change in entropy, I'm just going to write it in big deltas instead, is greater than the entropic cost of the reaction. And by algebra, this is equivalent to delta H minus T delta S is less than or equal to 0. Okay, so the idea is that if the system releases enough energy in, it doesn't have to use some of that energy for ordering or disordering. And if you're left with a negative, you have a set of leftover energy that you can use for your own purposes. Then there is a remaining amount of energy, of free energy, after paying the entropy tax. So if delta H minus T delta S is greater than 0, what that means is that the system doesn't generate enough heat for you to pay the entropic cost, and now there's a little bit left over that you need to pay to keep it moving forward. So if delta H is greater than 0, then there isn't enough heat to pay the entropic cost. So the system expects additional energy to complete this process. So a way I like to think about Gibbs free energy is that the free energy is a register, a cash register, all right? And there's some cost. The idea is that there's some cost that you have to pay to do something, T delta S, and you generate some money left, right? Think of it as like a budget, right? So you have some profit, right? This is delta H is your net, or it's not your net, it's your gross. It's the gross you get back, and T delta S is your cost. And so if you're left with a negative number, then that means that your costs are lower than your gross, and so you get some net left over for you to use. The system releases some excess energy for you to use, so it loses energy, hence the negative sign. But if the system doesn't generate enough energy to overcome that entropic cost, then you owe it energy for it to continue, right? So a negative means that the negative means that the system gives you energy back as a refund, and a positive means you owe the system energy for it to go to completion. Okay, so I've kind of gone around that in kind of a long, kind of drawn out way, but it's reasonable now that we have this idea that T delta S is a cost and delta H is a gross amount of energy, the gross amount of energy, and its difference is the net energy you get out of the system. Out of a process. And so if there's enough gross that you can pay for the cost, then the process is going to complete. But if there isn't enough gross to pay for the cost, then the system's not going to complete, right? It's not going to spontaneously travel to the final product. Questions about that? I know that was rather confusing. Once we tackle the numbers, it'll be a lot more straightforward. But the real idea are these two paragraphs, right? That the difference of these is it tells you how much energy your reaction gives out after completion, or how much you owe the system in energy. Bless you. Okay, so we probably, I'm kind of jumping around a little bit, but this concept of H minus Ts is what's called Gibbs free energy. Jesus Christ. Sounds like that fake voice of TikTok.
It does. That's fair. Want me reading Reddit's again?
Yeah. All right, so Gibbs free energy, this idea that we call G, Gibbs free energy of a system, is H minus Ts. Now it's very interesting that we learn Gibbs free energy. Gibbs is an American. Most of these developments were done by the Germans and the British, but Gibbs in some ways is the founder of modern thermodynamics. We'll see Gibbs' name come up a lot. And Gibbs lived here in New Haven his entire life. He was an instructor here, not at this university, but at Yale. This is, of course, the 1800s, when Yale was the only school in New Haven, really. He grew up here. He was raised here. He taught here. He died here. He published here. So in some ways, modern thermodynamics was founded here in New Haven. And his namesake, of course, is this idea of free energy, amongst many other things. Gibbs also was a mathematician as well and had a lot of success with mathematics. He wasn't very popular in America, right? He was a little old for a Nobel Prize, but he was never all that well known in America until after he died. He was kind of well known by the thermodynamicists and the physicists of Europe because he published in European journals. Actually, no, he didn't publish in European journals. He published in American journals. He published in local Connecticut science journals. And for some reason, the Americans never got a hold of those, but the Europeans did. And so the Europeans knew all about Gibbs for a long time, and this was a big deal. This was really clarified a lot about thermodynamics. It combines everything that we've done into one concept. And it wasn't really appreciated in America until the 20th century. But you can say that thermodynamics was founded here in New Haven, thanks to Gibbs, Josiah Gibbs. The chemistry building at Yale is still named after him, the Gibbs building. So the idea is that we can define what we call the Gibbs free energy of at any temperature T, and of course this is also a function of P and V, of course. But we don't have to worry about that so much because we're going to fix P to some value, and we're going to often talk about things that don't change volume very much. So in general, we think of this as a function of fixed T. Let's do a little bit of analysis on this equation. Just a little bit of calculus. And let's think about what happens when we vary G. Right? When we just adjust G a little bit, we put a little bit of energy into our system around. So dG is going to be derivative of H minus Ts. Of course, it's the derivative of H minus the derivative of T times S. Just as a hint, you have to take the product rule here, which is dH minus S dt minus TdS, right? You take the derivative of one, multiply it by the other, and then take the derivative of the other, multiply it by the other variable. S dt minus TdS. And let's think about what happens here when we fix temperature. So dt is equal to 0. Right, which is often what we do in lab, right? Often we set our temperature and go. And let me find a page for this. Yeah. Why am I not getting this? 7276. Oh, I'm looking at the wrong page. I'm sorry, guys. 73. 74, Okay, yeah, here we go. All right, so if dt is 0, this goes away. So dg is equal to the change in enthalpy minus T times the change in entropy. Of course, all this is delta G equals delta H minus T delta S. It's the same thing, but just in small changes instead of big changes. And we can write now what we can do is use the first law, and we can now expand enthalpy in terms of its definition. So now let's take H equals U plus PV. So we have dg is equal to the derivative of U plus PV minus TdS. So dg is equal to du, and we have to do the product rule for pressure and volume, so that's PdV plus VdP minus TdS. And now we can apply the first law, which is that du is equal to dq plus dw. So dg is equal to dq plus dw plus pdv plus vdp minus tds. We can make a really nice simplification is that we can assume, right, we're using enthalpy, so we're in isobaric conditions, right? Because remember, H is defined at constant pressure. So this term goes away. But, one more thing, but the second law says that dq is equal to TdS. Right? That's what the second law says for a reversible process. We'll just assume reversibility. So we can say now dg is TdS minus TdS. These go away. We're left with dw plus pdv. So what is this? So this is the work done by expansion, right? This is the work done by expanding the volume. But if we think about liquids when you don't do work on them because they're not compressible. So if you assume that this is 0, dg is equal to the change in work, the work that's available left over, right? And this is exactly the concept that I was getting at, is that if Gibbs free energy is a negative number, then that means that there's a little extra energy being released by the system that you can for work, right? This is energy that you can use. All right, let me write that down. So if delta G is less than 0, then delta work, reversible work, is less than 0, which means the system performs work in a spontaneous process. Right? The system, as I said, the system puts out energy. Right? That's energy we can use. But if delta G is greater than 0, then the amount of work that is put in is greater than 0, which means that the system requires work, additional work, to be spontaneous. Okay. Again, it comes down to the idea that is there an energetic refund or a cost associated with this process, right? If the process goes to completion, Is there a refund of energy that the system will give us? If the answer is yes, then delta G is going to be less than 0, and we get some workout that we can use for ourselves. But if the cost of the reaction, the entropic cost of the reaction is greater than the amount of energy the system releases, and delta G is greater than 0, then in order for the system to be spontaneous, you need to put work in. Right? The system says pay up. Right? In order for us to keep going, you got to pay. Right? And so that's the really nice thing about Gibbs energy, is that enthalpy tells us something about the heat, the total heat released from the system. Okay, so let's think about that. Enthalpy is the total heat transferred by the system. Entropy, S, is the amount of heat required to satisfy statistics. Right? Some statistic, right? Every reaction process is statistical, and there's going to be some change in the statistics. That costs energy to rearrange the system to a new ordering. Right? This is ordering. And so that means that G is what's left over by the process. In terms of energy exploitable by the user. So naturally, if we want to look for a process and we want it to go to completion without us having to put more effort into it, then we want to set up the system so that delta G is always less than 0. So that will drive the system to completion, or to something that looks like completion. Now, how much time do we got? 20 minutes. Okay. Now I want to think about something here. What happens if delta G is equal to 0? What does that mean? Well, let's think about, again, a reaction A plus B goes to C plus D. If delta G is 0, right, that means that there's exactly enough energy in the system to pay the entropic cost, which means that is equally likely as the reverse reaction. Right? The only difference is we're flipping the initial point and the final point, so delta G just changed the sign, but if it's 0, then there's no sign to change, they're exactly the same. And so the idea is that the process to go backwards is equally as likely and has the same cost and benefit analysis energetically as going forward. Right? And we call this equilibrium, perfect equilibrium. So that means that forward and reverse are exactly the same process, and so we would expect to see A plus B and C plus D at the same time, right? Because for every reaction that goes forward, there's going to be equal probability going backwards, so in the end, you're going to get 50-50. Right? That's a perfect equilibrium. And of course, if delta G is less than 0, as we'll see with equilibrium, delta G is less than 0, then it's more likely for the system to go to products than it is backwards, so you would expect to see more products than reactants. So same analysis, some gen chem. There's a different way I'd like to look at this a little bit. A better way to analyze this, I think, is to think about molecular structures. So for instance, what's a good example? Yeah, let's think about this one. So, let's see if I can draw it. It's been a while since I've done this. Yeah, let's take a chair. All right, so let's take chair cyclohexane, okay? And let's put an X here. That is an H on this direction, right? And there's going to be an equilibrium between these. All right, we know this from chemistry that there's an equilibrium. Let's see if I can draw it. It's like this. Hey, that's not half bad. Where the X now is equatorial. The H is like that, right? And the question we have is delta. What is delta G? Okay. Now I'm going to make a claim in this reaction that. Right, so let's write that now again. That delta G is equal to delta H minus T delta S. Right? So there's going to be some energy difference between the two, unless X is H, then they're equivalent. So if X is equal to H, then delta G is equal to 0 because these are the same structure. We'll talk about that in a second. But if X is not equal to H, then delta G is not equal to 0 because they have slightly different energies. Right? So, but I'm going to say that delta S for this reaction is effectively 0. You could prove that, but they're effectively the same. Right? So delta G is on the order of delta H, which means, again, that if this is favored in this direction, then this means this is an exothermic change, right? Delta H is less than 0, it releases heat, and this is favored over this form. Or we'll call this B versus A. Right, so if delta H is less than 0, then B is favored. And if delta H is greater than 0, then A is favored. I want to look at this in a different way. This is just basic old analysis. Right? You can plug in AX, for instance, if X is CH3, delta H is less than 0. Right? Methyl prefers to be equatorial. And if X is F, then it's flipped, it turns out. H is greater than 0, it prefers to be axial, for instance. Right? But the way I want to look at that, instead of this kind of qualitative way with just some numbers, is to think instead of plotting energy, let's plot Gibbs free energy, as a function of some coordinate that transforms this molecule to this molecule. Right? So there's some path. Right? We have to move all the bonds around and stuff, but there's some path that takes us directly from A to B. Right? We don't know what that path looks like, but we know that there's a one-dimensional path that we can move. We move this up and move this down, and we get this structure. Right? So what happens? So let's write A here and B here. And we go and measure G for these two substances. Let's just say A is right here. Right? Right? And what happens as you start to move the system along the path? What happens to G? What happens to the energy? Well, in order to deviate the structure from its structure A, you got to distort the structure away from its minimum energy configuration. And so that means the energy is going to raise. And then eventually it's going to hit a middle ground, right? There's going to be a middle point where the energy is maximum, and eventually it's going to come back down into here. Like this. Right? So the energy goes up, and then the energy comes back down again. And of course, delta G, let me make this more obvious. Change in delta G is this energy difference right here. The system has somehow lowered itself in energy as it's gone from A to B. Okay, so if the molecule, so now let's imagine over time what happens here. Okay, we're gonna tackle this in much more detail when we get to kinetics and equilibrium, but let's kind of deal with it qualitatively. Right? What we're saying is that because let's say this is true, right? That G of A is greater than G of B, so delta G is less than 0. Right? Because GB minus GA is going to be a negative number, because GA is bigger than GB. Right? So the energy decreases, right? So we would expect this to be we expect this to be spontaneous. Right? But what we've assumed is that a system, right, let's say we start with a molecule right here in energy, has some way to get over this hill into here. Okay? So what that means is that in order for this to be spontaneous, the system must have enough energy to overcome this hill. Imagine the molecule is a ball, right? You have to roll that ball up the hill with enough energy to get it over the crest. And of course, once it's over the crest, it can roll back down, right? But what if it doesn't have enough energy? So for instance, again, where that energy comes from is thermal energy. So for instance, let's say RT is here, right? So the system on average has that much thermal energy just from temperature, right? So any molecule in A automatically has enough energy to be above the barrier, right? And so this would imply, let's call this barrier we'll call it delta G dagger, double dagger, which is what it's actually called. Is RT is greater than delta G dagger, right? It's greater than the barrier energy. So any particle in A that is in A form can interconvert, right? It can get over that barrier. Right? On average, each particle of A has this much energy, so it's naturally going to want to, again, the key point is that molecules, if able, the system will always achieve the lowest energy configuration. All right, so if given the opportunity, a molecule that's in A is going to want to move to B, because B is in lower in energy by this amount. Right, so if RT if the temperature is great enough to provide enough thermal energy to get you over that barrier, then this process is spontaneous and it's going to equilibrate. Right, you're going to start forming Bs. Right? How many Bs you form is up to, we'll learn that later, but you can imagine that if you start at A and you have enough energy to get over the barrier, then over time you're going to convert a lot of A to B. Okay, and so that's nice, right? So that's what we mean by spontaneous, that the system will eventually has enough energy and enough probability that it will get from a higher energy point and go to a lower energy point, right? That's what we mean by spontaneous in this case. But now here's the problem. What happens instead? I'll draw with a different color. I'll draw with purple. Let's do green. Oh, let's do orange. What if the energy is here? What if the system is sufficiently cool enough that you don't have enough energy, right? And you start with A, right? You have a molecule that starts with A, but the system doesn't have enough energy to get over the barrier because on average it's right here, right? So even though the system you would predict to be spontaneous, right? So let me write that down. If RT is less than delta G bar, then although delta G is less than 0, right? The reaction difference between A and B is less than 0. There isn't enough energy to overcome the barrier. So even though our numbers about B and A suggest that this reaction is spontaneous, right? Delta G is less than 0, the system never has enough energy to go over the barrier, so it can't equilibrate. Right? So even though delta G predicts spontaneity, the system cannot achieve the process due to the barrier. Right? So in some ways, in chemistry, delta G only tells us half the story. Right? We can have a process, for instance, let's look at another example. This is actually a really good example. For instance, imagine we had a path, some coordinate. It doesn't matter what the coordinate is. Just some molecular coordinate as we rearrange a molecule from one to the other. And you have energy, you're plotting energy here. And maybe you have this local equilibrium like this. You have a small barrier. And let's say RT, let me write RT. The amount of available thermal energy in your system is here. We'll call this A, and this B. All right, so there's enough energy that you can get over the barrier, so the process of A to B should be spontaneous. G. But what happens if, for instance, you have another connection that has a huge barrier and a really negative energy, like this? Right, so if you just look at delta G of C minus delta G of A, you would expect all of your reaction that your system is going to spontaneously interconvert into C. Right? Because the energy difference is huge. You have a huge negative delta G here. But the fact of the matter is that the barrier, the amount of energy that you have to put into the system to overcome this transformation, maybe you have to break a bond or something, is so great that the system never equilibrates here. Right? The system traps itself here. Right? So the barrier to C is so great, the system never reaches it from A. Right? And so what we would say is that if we were to look at this, imagine that we had some spectroscopy, we did some spectroscopy, we looked at A, B, and C, what we would see is that A and B equilibrate. These are at thermal equilibrium. Right? You get the exact amount of B that you would expect by the delta G difference, the negative delta G, but the rest of these don't equilibrate. So there's no thermal equilibrium between A, B, and then C. Right? And this is what we call local thermal equilibrium, or LTE. Right? We have a system where the delta G's tell us, okay, everything should flow from A to C. But the assumption that we make is that the system can access all of these positions of equal probability. Right? Everything's random, right? So if the system is randomly moving between all of these orientations, for the system to be, all of that to be true, the whole system has to be at thermal equilibrium. Let me write that down. In order for the spontaneity criterion to be true, the system must be able to access all possible states. Right? So a system that starts in A here can access B just fine, but it can never access C, despite the fact that we predict C to be the lowest energy form. And the reason why is there's this massive barrier right here. Right? There's never enough energy in the system from collisions, or just from the thermal environment to get over that barrier. So the system never randomly samples C. It's as if it doesn't exist. Right? This is a wall, a thermal wall. Right? So in order for delta G to mean anything to us, right? Of course, when we see that delta G between A and C is negative, that's great. We know that this is lower energy. But in order to see that in practice, in order to see for that spontaneity to realize, you need to be able to get past this wall, right? You need to be able to sample every single point in this space, A, B, and C. And the fact of the matter is it just can't. And there's a lot of really, really good examples of this, right? So let me write down these two concepts because they're important. Two very simple concepts. The idea is that thermal equilibrium implies all points in an energy space, right? In energy space, I mean, say, a molecular coordinate versus energy, be accessible. A local thermal equilibrium is one where only a subset of arrangements or states are accessible. A global thermal equilibrium is where all are accessible. All right, so we have to be really careful. And so the idea is that spontaneity between 2 points, between an initial and final point, using delta G as our measure, only applies to regions that are in thermal equilibrium. There's a really good example of this. For instance, there are a number of reactions, and we'll look at these as we go on. There are a number of reactions that have very high, for instance, a really good example is the formation of nucleobases. Right? So the things that make up DNA. The things that make up, so adenine and guanine in particular, you can show are made by, there are oligomers, right? They're combinations of multiple molecules of HCN. So guanine and adenine can be expressed as HCN, well, ATCG, A and T, A and G, I think, can be written as HCN to the N, right? They're oligomers of hydrogen cyanide. And it turns out if you look at the mechanism of adding HCNs together to form adenine and guanine, the whole thing is downhill. So this is, imagine this is HCN plus HCN by themselves. This is HCN2 plus HCN. So 3 HCNs by themselves. This is 2 HCNs plus an HCN, and this is HCN3. Right, and you keep going. I think you need 5 of them. And so people wonder, one of the things that astrobiologists in particular consider is, well, where do the nucleobases come from, right? What's the originating chemical source for biological materials? And what they found is that you can come up with a mechanism that says, let's add 5 HCNs together to make adenine, and it works great. It's all downhill. Every step you add an additional HCN and oligomerize goes downhill. And people thought that, well, that must be the reaction. Well, the problem is that in the conditions where these molecules are formed, the temperature is very low. So there's not a lot of residual energy in the molecules because it's often at 10 Kelvin. Sometimes they're in the vacuum, so they can't collide with things, so the collision parameters are very poor. But typically they're in cold environments. And the fact of the matter is that even though this is a downhill process, you never see HCN3 or HCN4 or adenine in the interstellar medium. You don't see these big oligomers in the interstellar medium. Because the energy, the barrier to go from 2 to 3 is so massive that it's impossible to achieve that in space. So there must be, so that means that even though that there is a mechanism that is downhill energetically, spontaneous energetically for forming adenine and guanine, the barriers are huge. And so it's not entirely clear how these things are made because there's no way physically in space to be able to get over these walls. Right? So the system can't equilibrate. Right? So even though there's a possibility to, right, if we waited forever, infinite amount of time, maybe everything will move this direction, we just get lucky. The fact of the matter is that's never happened. We've never been able to observe these large oligomers of HCN in space because the barrier is just so big. It's so rare. Right? And so delta G only tells you half the story. Right? Delta G only tells you that if you're able to access every point in this space, where everything's going to flow spontaneously. Right? If we had infinite amount of energy, right? If our molecule is way up here in energy first, well then we could access all of these independently, right? So probability to fall in here, probability to fall into B, probability to fall into C. And of course it would probably fall into C the most because that's the most negative energy, the most spontaneous. Right? And that would imply that this whole system is in global thermal equilibrium, right? All of these states can be accessed equally. The fact of the matter is that in real life, or in a normal situation, that's not always the case. And so your system might be in a region where it can only access a portion of the things that are accessible, and so you get locked into a specific arrangement. So even though B plus C is spontaneous, there's never enough energy to go over the board. Right? So delta G only tells you theoretically how a system will evolve in time. Right? But you have to understand more about the system in order to understand your environment to know if it actually happens. Right? So delta G only tells you half the story. Okay, we don't often have to worry about this because when you're in organic chemistry or you're in regular chemistry, you're doing things in liquid at room temperature. There's usually plenty of energy, lots of collisions. Solvent effects allow you to have enough energy to go over these barriers. So we often use delta G to measure things in liquid phase very often at room temperature because we often have enough energy. But there's a very, very, very large amount of chemistry that can't be done that way because you don't always have this amount of energy. You don't have enough energy to go overcome these barriers, and so you never have global thermal equilibrium, which means that delta G only tells you the sign of any energy difference, but doesn't tell you anything about the probability for B to convert to C. Okay? So the answer to that question is how do we measure that? What's the probability that B will get over this giant barrier to C at some temperature? And kinetics will tell us that problem. Kinetics will end up being proportional to the energy difference of the barrier to the minimum, right? How much energy has to overcome, and that's the speed at which a reaction occurs. Right? That's kinetics. So delta G only tells you half the story. Right? Delta G will tell you that all things being equal, C will be the most likely product. But the fact of the matter is not all things are equal, right? It depends on the conditions, it depends on the context, it depends on how long you're willing to wait for the system to evolve. So delta G really only gives you a little hint. It tells you that it's spontaneous, but only if it's accessible, right? But not every state is accessible. Okay, we're out of time. So we'll come back to this idea a little bit and talk about measuring delta S and delta G for molecules, talk about how delta G changes with temperature, and that will get us at a perfect place to talk about phases, which is my favorite topic of the course. So we'll jump into phases next week. Yeah, you too. Thank you.
Okay. Here,